Okay, new unit, transformations. Oh, this is gonna be good. Okay. Um, Transformations are about how we can take things in the plane. We can take things in geometry and we can apply some instructions sort of to those things and they will move around. And it's basically the language of things like animation and in video games and all that kind of stuff, where you get one figure to move onto another one and define some sort of motion. Sometimes they call that mapping, and in fact, it's a little bit more of a grown-up kind of mathematical term to call it a mapping, a before and after picture. And that's what the mapping does. Mapping tells us all the instructions we need to know to move from that before picture, which we call the pre-image, vocab term down here, to the after picture, which we call the image. Let me read it to you the way it is here. Mapping in geometry is the same idea as a function in algebra. So in the functions in algebra, you had inputs and outputs, and this is kind of the same thing. A mapping is a correspondence between sets of points, while a function is a correspondence between sets of numbers. In a function, each number in the first set corresponds to exactly one number in the second set. Similarly, for a mapping, we write this. You get one sort of input point, and it comes out as an output point. This is the standard notation. M stands for the process. M is like the function notation that you're used to seeing from algebra. In algebra, you saw this. You saw like function on x takes the point x and it does something like 2x plus 7. And you'd have an input number. Usually we write these as ordered pairs. Say if I threw 1 into that function machine, it would spit out a 9 because it would put 1 in for x, and then the answer is what we get out here. So that tells me 1 is the input, 9 is the output. Same kind of thing here, but here we're talking about points. We're not talking about numbers. We're talking about points on a geometric plane. It started out life as point P, then we messed with it and we threw it into the M transformation, and it spit out this point we call P prime. And P prime is the standard notation for what we would use for an output. It's nice that we use the same letter here for this new point, because then you can kind of tell where it came from. P going in comes out as P prime coming out, which is kind of a nice way to be able to tell later the befores and afters and the images and the pre-images. So the image of P is P prime. Again, the input part we would call the pre-image, and the output part we call the image. So the image of P is this, and P is the pre-image of this. Each subsequent mapping is named P double prime, and so on and so on. If you were going to do this in Sketchpad, it automatically puts on those types of notation. So if I put P prime into another function or another transformation and found a subsequent image, we would call it P double prime, because it's been operated on twice then, or 3 times or 4 times. Then there's one other layer here. A mapping from set A to set B is called one-to-one if every member of B has exactly one pre-image in A. We'll get to that a little bit later. Mappings might be one-to-one or they may not be. So one-to-one is kind of an adjective we use to describe some mappings. I relate it to birthdays, so we'll talk about birthdays later. All right, mapping G maps each point x comma y to point 2x y minus 1. All right, here's an example of a geometric mapping, but using coordinate points. Now, they don't always have to use coordinates. Most of the ones we're going to use this year are going to be coordinates, but they don't always have to be on coordinates. Believe it or not, coordinates often make these things easier to understand, if you can believe that. Ooh, whoops, didn't mean to do that. What did I just do? Can I fix that? Sorry. Okay, there we're back. Sorry, everything just kind of slid north. All right, find the images P prime and Q prime, so find the outputs of these as inputs. So we're going to throw 3, 0 into this machine, and this is what I mean, algebra kind of makes this easier, because here we're just kind of doing a double version of what you used to do in algebra. We throw the point 3, 0 into this process. This process takes any x, y, and it spits this out. So 3, 0 is going to come out when it goes through this process. It's going to turn the x's into 2x, and it's going to turn the y's into y's minus 1. And if I put 1, 4 into that machine, remember what that machine does? This is what the G machine does. It takes x's and it spits them out as 2x's, and it takes the y's and spits them out as y minus 1. So this point I would call P and I would call Q. These points I would call P prime and Q prime. All right, so that's all it is. Find the pre-image of r prime. So if r prime, I should probably write these on the other side. If r prime is actually negative 2, 4, where did it come from? What would have been the r that I would have had to throw in to have it come out this way? So this negative 2 is the result of 2x. Well, I can do this in my head. X would have had to have been negative 1 if it's going to go in the 2x process and come out as negative 2. And this y minus 1 came out as a 4, so I must have had to throw a 5 into that machine. Because it's 5 minus 1, it spits out as a 4. Does the distance from P to Q, okay, now let's start talking about some geometry. Does the distance, you know what, this bothers me. I should call this P prime right here. Do my notation correct. That's P prime, this is Q prime. I wrote them kind of after the fact. That was probably not legal. The geometry police are going to come after me. Okay. Does the distance from P to Q equal the distance from P prime to Q prime? Whoa, that's kind of a deep level thought here, because now these are, after all, points on the coordinate plane. What's the distance from P to Q? We just kind of have to compute these separately. Distance from P to Q, okay, P's at 3, 0, Q's at 1, 4. This is a Pythagorean theorem thing, like finding the distance between 2 points. I can let you look this up, but this is how you do it. The x distance, the y distance, you square both those things. This comes from a giant Pythagorean theorem, so we're actually getting something like this. This is 2 squared plus 4 squared, and I'm taking the square root. Oh my gosh, all right, this is 4 and this is 16. This is the square root of 20, this whole big distance. The distance from P to Q is the square root of 20. The distance from P prime to Q prime, so I do the same thing, distance from P prime to Q prime. And you know, why would we ask this? PQ on the coordinate plane was a segment. There was a distance from P to Q. I threw those points into this ringer and they spit out new points. I want to kind of find out, well, did throwing them into that machine change the distance between them, or did they come out and were they the same distance? And we can maybe draw this. I know I stopped in the middle of this conversation here, but PQ originally, okay, P was at 3, 0, so P was kind of there, and Q was at 1, 4, so Q was kind of here. Originally, they were kind of like this, and that was a certain distance. I'm totally freehanding. This is gonna be odd. This is gonna be horrible. And P prime was more like out here somewhere, and Q prime was like 2. That was 3, right? So 2, 3. It's like Q prime's up here somewhere. So it looks to me, just kind of like by freehanding, it looks like it kind of got longer when we put it into this machine. Maybe that 2 had something to do with it. Well, we'll see. The distance from P prime to Q prime, again, it's a huge square root of. I'm going to use the 6 and the 2 together, and I'm going to use the negative 1 and the 3 together. I'm mixing some of these up in order. You know what? Sue me. You're going to get the same answer. All right, and then this is 4 squared. This is also 4. Distance from negative 1 to, yeah, it's also 4. So this is 16 plus 16. This is the square root of 32. So as we suspected from my really bad freehand drawing, they are not the same. This one's a whole lot longer than this one. So this one does not, when I use the G mapping, I don't always get the same length segments. When I throw this segment into this G machine and it spits out a new segment, it may not be the same length. All right, first type of like generic class of transformations we're going to talk about is a reflection. This one, if you're used to the name reflection, you're like, oh yeah, I could reflect a figure, I could rotate a figure, I could translate a figure, and you're used to those. If you've taken animation classes or if you've talked about geometric reflection or geometric transformations before, you might be used to some of these types of things. This one we just made up here, this first example, it was nice because it was a general example, but this one really doesn't have any name. There was no special type of reflection this was. It was just, let's put these let's take this algebra process and kind of do this in general and see what happens. It turned out to be kind of a bizarre one because it didn't even make the distances the same. Reflections are going to behave a lot more predictably. A reflection is a type of transformation where you use a line called the line of reflection. You can think of it kind of as a mirror line. And it's defined this way. Each point of the pre-image and its corresponding point on the image are the same distance from the line. If you think about that in terms of you looking into a mirror, I mean, this one really is about there being the idea of a mirror. If there's you standing there looking at the mirror, okay, this would be horrible also, but there's you, there's your nose, here's the rest of your face. All right, there's like your silhouette, and you're looking into the back of your head, I suppose, so you can tell it's a person. There's some hair. All right, so if you were to Don't laugh. If you were to look at yourself, so I guess you need eyeballs. You're gonna look at yourself. You're looking at yourself in the mirror. If you ever think about the person you see behind the mirror, so I'm taking like a cross section view of you looking in your bathroom mirror. So here's the wall that the mirror is on, and you look into the mirror and you see a fake person in the mirror. And okay, the fake person in the mirror should look something like you. So hopefully I can draw this somewhat. Okay, it's not great, but there's an eyeball, there's some hair. You're looking at a fake you in the mirror. And you see a fake you in the mirror, and that fake you in the mirror is actually kind of behind the mirror. What this first sentence is saying is whatever distance that the fake person is in the fake universe behind the mirror is the same distance as you are from the real mirror. And you notice as you get closer to the mirror, as you move your nose closer, the person in the mirror starts walking up towards you also, and you touch noses at the same point in the mirror. And if you move farther back, that person moves farther back also. They're the same distance away from the mirror. It's a little easier in 2 dimensions what we're going to be doing with geometry, but you can think of that idea. Reflection is one of these types of transformations we're going to refer to as an isometry. A transformation where, you know how we had this problem back here where the distances didn't stay the same? If the distances do stay the same before and after, so that like the length of this hair, whatever this hair length was, after I reflect it, the length of the hair in the mirror, if you could measure such a thing, I mean, kind of theoretically, it's the same length hair. You don't look like you have shorter hair in the mirror, right? You have the same length hair. So since the lengths are preserved, and it's every length in the picture, not just that one hair, but the length of your nose, the length of your, the height of your eyeball, like all that stuff is exactly the same length. That's called an isometry if that's going to happen throughout the transformation. And reflections will always do that. And if that's true, we can also call that a congruence mapping. So we're going to know that the figure over here, as bad as it looks, I know it's a hand drawing, just cut me some slack. This picture is supposed to be congruent to this picture if it's really a reflection. Let me show you this in GSP because it's a lot snazzier and it's a lot more like what we're going to be doing. All right, so here's a little, it kind of reminds me of Phineas's head from Phineas and Ferb. And if I draw the reflection of that, this is what we get. So this is the original pre-image over here. Here's the line of reflection, and here's the image reflection over here. What's cool about Sketchpad is, of course, I can change this. I can move my Phineas closer to the mirror, and they touch noses. I can change this shape so it's completely different. Whoops, didn't mean to do that. And I could start over and show you what this is like. So this is the before picture. It's reflected, perfect mirror. It's over here. Oh, yeah, and if you move farther away from the mirror, notice how it goes farther away. If you move closer, oh, and this is going to blow your mind. Watch this. Whoa, they can even do that. Notice I always have a symmetric picture. Okay, here's also another weird thing. I like the original shape because it could tell you kind of that this one's kind of backwards from this. That's the next thing in your notes. Also, what's interesting about this is you can actually move the mirror. If you move the mirror, it moves the reflection piece also, which is kind of going to freak you out for a while. But I'll come back to that for sure. All right, so reflection does not preserve orientation. That's just saying about being backwards. Orientation refers to the arrangement of points relative to one another after a transformation has occurred. So you might be able to tell from this picture already that every single distance in here is the same as every distance in there, but this one is somehow backwards from this one. If I was to, and the explanation in the notes has something to do with labeling points and that kind of thing, but I just think of it this way. If say you had a stamp that would stamp this thing out, could you use the same stamp to stamp this one? And the answer is no. You're going to get, you need to get a backwards one for this. And you know this from living around mirrors your whole life, that when you look at something in the mirror, it's backwards. You can't read the word on your sweatshirt in the mirror because the mirror reverses it. So we say that the orientation of that object has been reversed. When we talk about the, comparing the pre-image to the image, the orientation has not been preserved. Okay, that seems like a good place to stop. This is going to take definitely more than one part. See you in a second.